Okay, they know what's going on. Okay, go ahead. I have Rahul today and with no props, but I'm sure it'll be an exciting talk.
I thought about trying to get a wheelbarrow, but I didn't think it would fit in my car, so it would be crazy. It would be nice to have one.
Facilities, I'm sure they would have looked you one.
Oh, yeah, that's true. That's true. Okay, so this is joint work with Alex, who I guess you'll be hearing from soon, maybe in the next month or so. I don't know. Yeah, so I'm going to tell you about why obfuscation is a wheelbarrow, and just to give you some preview about what we're going to do. So actually, I use this slide a lot. I used it in Berkeley, and Yuval Shai asked me, he's like, Rahul, do you know what this is? I said, oh my God, I'm not that old. It's a microwave. Like, anyway, so we'll start with what is I/O. I/O will stand for indistinguishability obfuscation. And then we're going to move on to Charles Dickens, and we'll talk about Hanlon, his great-grandfather, and then we'll have 3 different columns. Okay? Any questions about what we're going to do?
Who's my great-grandfather?
Yeah, actually he'll show up twice. Yeah, he's an important character at the top. Okay, so what is my goal? So my goal is this. So who's this guy? Anyone know? Everyone knows. Scooby-Doo. Fred. Oh shoot, I guess I got it wrong. Who's this guy? I guess this guy is cryptography. This guy, I want to argue, is indistinguishability obfuscation. And I think indistinguishability obfuscation really turns cryptography into complexity theory. Like there's kind of this phase transition. These cryptographers define this notion I/O. You don't need to know what it is yet. I have a bunch of slides on it. But like the main takeaway I want you to have is that like this notion kind of secretly has turned cryptography into complexity theory, which I guess for this audience is great. Yeah, this is like some good arbitrage. Yeah, well, yeah.
Is there something I should know about this Fred guy that you're using?
No, I won't use no background of Scooby-Doo assumed, no prior background. Yeah, oh, self-contained Scooby-Doo background. Okay, so my goal in this talk is to try and illustrate this phenomena, assuming as little background as possible. Okay, so I'm hoping that you won't need to know much about cryptography before this talk. I'm going to tell you everything you need to know. It will also come at the cost of, I'm not going to tell you like maybe our results in detail. We'll actually have kind of a lack of formal theorem statements, and I also won't highlight the most technically interesting parts of the thing because I just want to illustrate this phenomenon. In fact, I'm going to tell you kind of the technically least interesting parts of this thing because my goal is not to convey what's technically interesting. My goal is just to illustrate this phenomenon. Okay? And then, so that's my goal. I also have a secret other goal. My other secret goal is this. So who knows what this is? Yeah. Okay. Spoilers. Yeah, I guess I only have a few characters, so you always know what I'm going to do. So, in The Lion King, there's this famous song where the main character Simba goes and runs off from his duties. He's supposed to assume, the kingdom. He's supposed to be the king of the animal kingdom, but he decides to run away. He finds these 2 fun characters, Timon and Pumbaa, and they have a different life philosophy than maybe Simba's dad would like, which is that like they like to relax. These 2 words will solve all your problems. Hakuna Matata, what Pumbaa says. But actually, if you listen closely, this is not what Pumbaa says. Pumbaa says if you listen really closely, what he says is these 2 words will solve all your problems, indistinguishability obfuscation. Okay? So hopefully I'll illustrate to you in this talk that this is actually a really powerful tool for complexity theory also. So then you can use this hopefully to solve your favorite problems also. So these are my 2 goals. All right. Cool. Any questions so far? Any technical questions?
Is there a problem session at the end where we come to you and you solve all our problems with your...
This is a take-home exercise. Yeah. Okay, great. So now I want to do, I'm going to do a complexity crash course and then a crypto crash course. Okay. So complexity crash course. Good. Circuits. We're all we all like circuits. In a circuit, you have a bunch of different gates. They compute simple operations, and then you can combine them to compute more things. And you talk about their size being the number of gates. Okay, we all love circuits. Okay, what do we need from complexity theory? So in complexity theory, one of the things you're interested in is like for a particular subset of all binary strings, which you usually call a language. You can think of it as a decision problem. There is some input X, and then you want to decide whether it's in the language or not. And there's a bunch of different complexity classes you can define on languages. Or maybe the favorite one is P, which is like, those languages which you can decide whether something is in the set or not in polynomial time. There's also another famous complexity class is NP. NP is defined as those languages for which you can like certify membership in L in polynomial time. But, really you should just think of this main example, which is SAT, which is just circuits for which there exists an input on which it evaluates to 1. And how do you certify that something is in SAT? You just hand me an input on 1. And then the last complexity class that we're going to use in this talk, and this maybe is a complexity class you might use less, is co-NP. So co-NP is not the complement of NP. It is like the complement of the languages in NP. So like, for example, the canonical co-NP problem is unsat, which is those circuits for which they evaluate to 0 on every input. Okay? Okay. So hopefully that's a review. And the main conjecture, or some of the main conjectures in complexity theory is that, for example, this like picture is kind of accurate. So that we believe that P is not equal to NP, and that turns out to be equivalent to this particular problem, SAT, not having a polynomial time algorithm. And we also believe that these two sets, NP and co-NP, are not equal to each other. And that corresponds to SAT not being co-NP. So this statement really says that if you want to certify that a circuit evaluates to 0 on every input, there's no short certificate I can hand you. Okay? All right. Any questions about complexity theory? All right, cool. And yeah, just a disclaimer. AMUOA. Yeah, everybody know what that stands for? Anyone know what that stands for?
Ask me.
Oh, you're on the right track. Actually, this acronym's I put this up there for you. I put this up there for you. There's a disclaimer in this talk. I'm gonna always minimize use of acronyms. Okay. So, okay, for the experts in the audience, sometimes you want to make a complexity class by putting a /poly. Sometimes you want to make it a randomized complexity class by putting a BPP. Sometimes you want to talk about like an infinitely often complexity class. I'm not going to do this. Either you know what that is, in which case I'll assume you're an adult and you'll be able to see, oh, this is supposed to be a /poly, there's supposed to be an infinitely often, blah, 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 or you don't know what this is and I don't want to confuse you. Oh. Okay. Good. So I'm going to try and minimize my use of acronyms. And by doing that, I'm going to conflate like P and BPP and P/poly and P and stuff like that. So if you know what those is, great. If you don't know what that is, don't worry about it. Okay, cool. So that's my complexity crash course. Okay, now we go into the cryptography crash course. And so I'll start off with a disclaimer. This is a disclaimer if you're like more of a math person, but like me, and you haven't seen too much cryptography. So who knows who this guy is? Nice.
Winston Churchill.
Great. And what is Winston Churchill famous for? Well, one of the quotes he's famous for is this: "Never in the field of mathematics has so much been assumed by so many based on so few theorems." So cryptography is a field where like we really don't know how to prove almost anything unconditionally. So almost all of the objects that I'm going to talk about in this like crypto crash course are things we don't know how to prove yet. Okay, great. So the most important notion in cryptography is probably this notion called computational indistinguishability. And it says kind of the idea is if you can't distinguish between two things, they're the same. And I was thinking about who to attribute this to, and there's lots of people you could attribute this to, Macaulay, Goldwasser, Yao, Adi Shamir. But maybe it goes back to the Turing test. At least one argument you can make is the Turing test, which says that, oh, if you can't distinguish a human from a computer, then like the computer is just as good as a human. Although actually, apparently this idea goes back even further than Turing. Goes back to this guy. Anyone know who this guy is?
Leibniz?
Yeah, this is Leibniz. He has this thing called the indiscernibility of identities or something like that. It's like one of the things he's famous for. One of the two things he's famous for that we'll see in this talk. Actually, three things. But he has this notion in philosophy, which is like, if two objects have exactly the same properties, every attribute is the same, then they're the same object or something like that. Anyway. So what does this mean operationally in cryptography? So this notion of computational indistinguishability is usually played on distributions. So let's say you have a distribution on n bit strings d, and another distribution on n bit strings d prime. We say they're computationally indistinguishable if for every polynomial time algorithm, when you draw a sample from D, the probability that this algorithm outputs 1 is roughly the same as when it outputting 1 if you draw it from D prime. Okay, so this is saying no algorithm can distinguish between these two distributions, and you could imagine, well, okay, if I can't distinguish from these two distributions, then that'll mean in some sense that they're maybe for the purposes of cryptography the same. Okay, and polynomial time here is just one setting of parameters. Sometimes later in the talk, we can also talk about larger adversaries and larger distinguishing probabilities like sub-exponential. Okay, great. So this is computational indistinguishability. Any questions about that? Great. So let me give you a first example just to illustrate this notion of computational indistinguishability, and because it's something that'll come up later in the talk. So it's the idea of a pseudo-random generator, okay? And so a pseudo-random generator is going to be a polynomial time function that maps, let's say, n to the 0.01 bits. 0.01 isn't so important here, just needs to be some number significantly less than n to n bits. And we want this algorithm to somehow, even though it only gets like n to the 0.01 inputs, to map to like random looking strings. So that in particular, the two properties we want is we want this algorithm to be efficient, it runs in polynomial time. And the second property we want, I've expressed kind of succinctly here, is some sort of pseudo-randomness property, which says that if you look at the distribution induced by running G on a uniformly random bit string of n to the 0.01, that's computationally indistinguishable from uniform on n bits. Okay? Good. Any questions about this? Hopefully this makes computational indistinguishability quite clear. Good. So this is one notion. And this is one notion of a lot of notions in the cryptographic universe, most of which I won't tell you about, but there's like a whole slew of things like one-way functions, pseudo-random generators, secret key encryption, bit commitments, zero-knowledge proofs. Actually, kind of interestingly, all of these notions turn out to be equivalent to each other. They all live in this world called minicrypt, but there are also many, many more primitives like collision-resistant hash functions, non-interactive zero-knowledge, whatever. Anyway, there's a whole slew of cryptographic universes, or objects in the cryptographic universe. And obviously, I'm going to try and minimize telling you about them. So, but this one object here, one-way functions, is particularly important. Okay, so it turns out if one-way functions exist, then like a whole slew of important cryptographic objects exist. So I'll tell you a bit about those. Okay, one-way functions. So a one-way function is a function that maps n bits to, let's say, poly n bits. I'll assume it's greater than or equal to n. And the guarantee you want on a one-way function is intuitively as follows. It's some function that's easy to compute in the forward direction, but difficult to compute in the reverse direction. Okay? So what does that mean? So what does it mean easy in the forward direction? We just mean that f is computable by a polynomial time algorithm. What does it mean to be hard in the reverse direction? What is the one-wayness of this function? We say that like for every efficient adversary A, every polynomial time algorithm A, if A wants to invert F on a random element of the image, so you draw some input x and 0, 1 to n uniformly at random. You run the one-way function on that to get y. Your chance that the adversary, when given y, comes up with a preimage of y under f is small. Okay? Okay, maybe just a show of hands. Who has seen this definition before? Just so I could calibrate. Oh, okay, good. All right, cool. All right. So it turns out this is kind of the minimal object needed for interesting crypto. And also kind of interestingly, so information theoretically, if you can compute something in the forward direction, you can reverse it, at least if you don't care about getting exactly the same preimage, but just a preimage. In some sense, a one-way function existing is like some sort of violation of an information theoretic idea. And you can think of crypto as like some sort of weaponization of the failure of information theory in the computational setting, and you can use it for fun and profit. Okay, great. All right, so this is the crypto background, all right? Or my crash course in cryptography and the crash course in complexity theory. Any questions about this? I guess. Great. All right, so now we're going to move on to obfuscation, which is the protagonist of this talk. And yeah, it's like I think Nir-Batansky has this title. It's like obfuscation is like somehow like the power of unreadable code. So like usually we think unreadable code is bad, but it turns out, at least for cryptographic purposes, it can be good. All right. So who here knows how to write code, or who here has written code before? Okay, pretty good. Wow, so more people know one-way functions than have written code before. That's nice. That makes sense. Okay, yeah. Who here has written a C program before? Oh wow! Wait, that seems like a superset of. Okay, so a lot of you raised your hands. What does this code do?
Oh.
Yeah. Anybody have a guess?
Is it print hello world?
That's a great guess. That's a really great guess. And yeah, it's a really great guess. It does not print hello world. Any other guesses?
Turns a 0 to a string.
It does not. That's another good guess.
See a put char there. I don't know.
Okay, so I've given you access to this code, and it seems like you weren't able to do very much with it. But now, hopefully this works. Let's see. Now, oh no, destroy my. Okay, hold on. Give me a second. Let me give you Oracle access to this code. All right. Sorry, I can't see. What button do I have to hit? I have to hit run. All right. Now I'm going to let you query this program on an input. Who has an input?
How many inputs does it have even?
Oh, it takes strings as inputs.
Okay.
Who has an input?
0.
0? Okay, nice. All right. Good. Proper. Anybody have a guess? What's happening?
Empty string?
Empty string? Okay, maybe you want to query on another input.
The number of dashes as the number of letters in the English representation.
No, but you're getting closer. Oh, but
Can we query Hakuna Matata?
Yeah, good. Sorry, I can't read what I'm writing, so. All right, now that is something of a guess. Morse code. Okay, great. Right. Good.
Wow, 0 is so complicated in Morse.
Yeah, I guess it's maybe converting it to ASCII or something like that. So this is Van Dorsler's winning submission to the IOC, not the International Olympic Committee, but the International Obfuscated C Code Contest. And this is an example that appears in Barak et al. So here I gave you access to some code, right? You have full understanding of what this function is doing. I've given you everything, you know. Nevertheless, it really wasn't helpful to look at the code, right? Like it was really everything we learned about it, we learned by running it, right? Like by having access to it. And this is kind of like a high level question in complexity theory is like, what is giving you the code of a program? What is giving you a circuit, tell you? Seemingly, all you can do with a program is run it. I mean, like you could read the code, but it seems very hard to analyze the code and understand something about it. And in fact, if you talk about like programs that are allowed to run an unbounded amount of time, we have like a very good formalization of this. There's like something called Rice's theorem. It says that if I hand you a Turing machine and I ask you kind of any semantic property of it about it, that's impossible to decide.
What is a semantic?
Yeah, good. It means that for any two Turing machines that are functionally equivalent, they'll either both have the property or both not have the property. Yeah. It's probably the definition you would expect, but yeah. Usually we care about programs or that we know will halt, or for something like a circuit, which like will not run forever. If I hand you a circuit, the maximum running time is at most its depth or something like that. And in the time-bounded setting, we also, we have things that like kind of smell along these lines. Like, so for example, the P not equal to NP conjecture, you could think of as like some baby version of this. Because like, what is the P not equal to NP conjecture saying? It's saying that stat is hard. What is stat is saying? Hard saying? It's saying, if I hand you a circuit, you can't tell if it ever outputs one. Okay? So at least that's like something in this regime of trying to formalize this, but actually we don't really have a great formalization of this. And this kind of motivate and this idea that maybe circuits are a black box, cryptographers thought it could be useful and interesting, which is what I'm going to tell you about next. Okay, obfuscation. So obfuscation as a concept, I'm sure it goes back for a long time, but at least in cryptography, it goes back to these two people. Anyone know who these two people are? I guess you know. Anyone else know?
Diffie-Hellman?
Yeah, Diffie-Hellman. Yeah, I don't know. I've always seen Hellman, but I've never seen...
He's the wizard.
Yeah. I also couldn't find any pictures of him without white hair. I don't know. This guy maybe is... Anyway, so Diffie-Hellman in there... if you don't know, there's like Diffie-Hellman had this crazy idea to come up with public key encryption, which was like at the time pretty nuts. And in fact, there's like a funny story where like they came up with it. And then like later on, Stanford realized like, holy shit, this is like an amazing concept and tried to patent it. But they like tried to patent it too late and there was a whole fight about it. Anyway, but in their paper describing public key encryption, they were like, it would be really easy to create public key encryption if we somehow could obfuscate programs. And if you're interested, I can tell you about what their reasoning is. But they kind of describe this idea. It's like, I don't know, if you like take some code and then you turn it into assembly machine code, it becomes unreadable and you can't tell anything about it. And that makes it really easy to turn like secret key encryption schemes, which are kind of easy to construct, into public key encryption schemes, which are like very hard to construct. But like the formal study of obfuscation began in this work in 2001 with a bunch of cryptographic all-stars. Let's see if I can name all of them. Boaz Barak, Oded Goldreich, Russell Pagliazzo, Stephen Rudich, Amit Sahai, Salil Vadan. Anyone know who this one is? Hey, Young. I couldn't find a picture of him. And okay, what's the goal in obfuscation? The goal in obfuscation is to turn spaghetti into spaghetti code, okay? So you're given some circuit C, and you want to scramble that circuit into some obfuscated version of C that hopefully, hides everything you possibly could about the circuit C.
So it's so
Good. Yeah, it's also a circuit. I'm going to give a more formal definition in a second, but yeah, I'm going to map a circuit to another circuit, and you'll also want the property that if this circuit
a
computed.
kid is generated using this problem.
Sorry.
A kid is
Oh
generated.
yeah. The kid. Yeah. This is one implementation. Yeah. And so it's going to map a circuit C into another circuit that computes the same function, but is hopefully obfuscated. And it turns out, there's kind of an ideal definition you would want here, a really great definition, maybe the first definition you'd want to come up with. I'm not going to tell you what the definition is because I don't have enough time. I want to tell you more things. But maybe, there's a lot going on in these parentheses. Maybe what you would want in your definition is somehow saying that if I hand you the obfuscated circuit, there's nothing you can do, nothing you can learn that you couldn't learn if I just gave you black box access to the C. What do I mean by black box access? I just, I let you ask for an input output, ask for an input on this input, what is its output? And if you're familiar with cryptography, you can come up with like a simulation-based definition to do this. I don't want to tell you about simulation-based definitions, but this is maybe the first definition you come up with. It's called virtual black box obfuscation. It's really great, and it just doesn't exist. Unfortunate. Which is unfortunate because it seems like the truth. Like if you go talk to a cryptographer, they'll be like, oh, fine, doesn't exist. But
The problem is that it's so general. Like if you want something more particular, like this.
yeah, okay, it's unclear what exactly the problem is. I mean, I can tell you a little bit about the counterexample. The counterexample is somehow like you make an obfuscated circuit eat itself somehow. It's like a Turing-esque diagonalization. It's easy to do this for Turing machines because like Turing machines, you can feed it the code of the Turing machines. It's hard to do this for circuits because how do you feed a circuit the code of a circuit? The input to the circuit is smaller than the, but it turns out you can do some like crazy trick with homomorphic encryption. Oh, if you know what that is, and you can make the circuit eat itself. If you don't know what that is, it was a really brilliant idea because today we know that we have constructions of homomorphic encryption, but back then they didn't even know that homomorphic encryptions exist. So like, and I think it was oh, okay, it's recorded. Okay, but someone had a really brilliant idea. Anyway. Okay, great. All right, so you have a notion. It's really great. It seems to describe reality, but it doesn't exist. So what happened? In the same paper, they defined a different notion of obfuscation. They were like searching for other notions of obfuscation. In fact, this is one of several that they mentioned in the paper. But this is called indistinguishability obfuscation. And it's kind of a very strange notion. It's like obfuscation for functionally identical circuits, okay? In particular, it's some randomized polynomial time algorithm. It's going to take as input three things. It's going to take as input a circuit. Maybe we'd expect that. And then it's going to take two other inputs that usually I'll suppress. But one is like the randomness, the internal randomness of the algorithm. And the other is you can there's this thing called the security parameter, which like controls how strong of a security you guarantee you get out of it. We'll once I go through the definition, it'll be more clear what those things are.
The algorithm is really deterministic.
Yeah, so so it's a deterministic algorithm, and where you put it also takes a randomness. Yeah.
Rahul, you worked so well for the mathematicians to understand, but you wrote one to the lambda as if.
Yeah. Oh, very good. Good catch. My bad. So yeah, you might think one to the lambda does not mean 1 raised to the lambda power, which would just be 1. I think. Is there anywhere where that's not true? But here I mean the string 1 concatenated lambda times. Okay, good. And so then you have two requirements of this to be an indistinguishability obfuscator. The first requirement is that the I/O run on a circuit C will output another circuit that is functionally equivalent to C. So these 3 lines here mean they compute exactly the same function. And it's perfect functionality. This needs to hold with like probability 1 or something like that. This always holds. Okay, great. Seems like you'd want that. The second thing is security, which is a kind of strange thing. It says, if you hand me 2 functionally identical circuits, C and C prime, of the same size, then the distribution of obfuscated circuits I get from C is computationally indistinguishable from the distribution of obfuscated circuits I get on C prime. So if I start off with 2 functionally identical circuits of the same size and then obfuscate them, you can't tell which one I started with.
You have to be same size, like.
Yeah. So it's like the reason kind of is like, imagine this guy was really small. Let's say this was of size n, and this was of size n to the 1000, right? When I obfuscate this one, well, this obfuscation algorithm runs in polynomial time. So this is going to go from like n to, I don't know, n cubed or something like that. But this one was only fed a circuit of size n to the 1000. I mean, unless it can like minimize that circuit, it's going to get, yeah. So it's like if I hand you a circuit, at the very least, I'm giving away some bound on the running time of computing it. So I have to kind of bake that into the definition. Yeah. Sure. But you're right. I mean, it's a very finicky thing because, like, I mean, if I have a circuit that has one more gate, then this provides no guarantee a priori.
So, okay, so what you're saying is that you really want the same size. The reason is that if there's a big deviation in size, then you have a problem. But if you have one more gate, you still.
Yeah. Well, what you could do is whenever you hand me a circuit of some size, maybe I like will pad it with extra dummy gates so that it will, yeah, and then you can kind of, yeah. Okay, great. Any more questions about this definition? Okay. And I will say, you know, before when I said we talked about computational indistinguishability, usually it was polynomial time. For I/O, it turns out in many applications you'll want this to be sub-exponential. I won't care about this too much. Or this will be important, but I'm not going to stress it too much. And okay, let me tell you two things about this. First is the following fact, which is strange. If P equals NP, which usually kills all of crypto, then I/O actually exists, okay? And there's this really strange thing you can do, actually, which relates to what I was saying you couldn't do to Yotam, is that if P equals NP, it turns out there's a way to just like, given this circuit C, just output like the lexicographically first smallest circuit that computes the same function. Okay? Like one way to get an indistinguishability obfuscator is, hey, I'm just going to hand you the first circuit that computes the same thing. This is a little strange. But hopefully, if you understand, this fact shouldn't be too hard to see. And if you see it, that's like a good check that you understand it. Yeah.
So if I'm iterating through all circuits,
Yeah.
can I test whether a given circuit
Good.
is actually equivalent to another one?
Yeah, it's hard to test. In fact, it's co-NP hard. But if P equals NP, this is like, yeah, if P equals NP, you can do a lot of things. Yeah. So this is actually always this satisfies both, you know, this algorithm output the Lex first thing always satisfies these two guarantees. The question is, can you do it in polynomial time? That's where you need the P equals NP part. Okay, great. And, you know, one, you know, remark related to this is that like you could think of I/O is like a circuit pseudo-canonicalizer. Like if one way to get I/O is always canonicalize the circuit, give it a Lex first one. But of course you know, if you believe P not equal to NP, then it turns out like you shouldn't be getting the Lex first circuit here, but it's some like way to like pseudo-canonicalize this circuit. Okay, great. And okay, so this is a definition. Hopefully you understand it, but you should be a little mad about it. Okay, who knows who this guy is? You know?
No. The tests don't stop. Like,
Wheelbarrow?
Oh, that's a good guess. That's a good guess. Okay. Anybody now have a guess?
It's a valuable.
I don't think
Dickens?
Good, Dickens.
Where's the time?
So Dickens doesn't like I/O, or at least in this part of the quote, he doesn't like I/O. And I mean, you look at I/O and you're like, okay, fine, you can. That's a definition. That is a definition. But on the previous slide, we were saying every circuit should look at a black box. Clearly, this is not the right definition, right? Like obfuscation for functionally identical circuits. Okay, fine. If I have two circuits that compute the same thing, I can obfuscate them. I mean, what's the point of that? Why is that useful? Doesn't seem very useful. Like, how is that going to help me build public key cryptography? I don't know. Like, seems very like a very weak guarantee. But okay, Dickens will have more to say about this later. Okay, good. Oh yeah.
Okay, you're just going to.
Yeah, this is some foreshadowing. Okay, you'll see that the actual quote is like for pseudo. Okay, you want the suspense? All right. All right, good. All right, good. All right, yeah. So Dickens says this is a bad definition at first, and yeah, you're like, I/O. What is it good for? What can we do with this thing? And as the song suggests, what is it good for? Absolutely nothing. Until 2013. So until 2013, you know, this was kind of a fun definition. You know, they had made it in 2001, but no one really knew how to do anything with it. And then a phase transition happened in 2013, starting with the work of Sahai and Waters, which actually said, hey, you could use I/O plus some complexity assumptions, which we'll see, in order to get pretty much everything you want in crypto. And, one-way functions, public key encryption, functional encryption, like rooted secret sharing, things we didn't even know how to construct from any assumption before you could get from I/O. And it turns out like people even started calling in this I/O like cryptographically complete. It seemed like any functionality you want, you could get from I/O plus some like minimal other assumptions. Okay, so it seems like you could get everything from it. But of course, we don't want it just to be useful. We want it to exist. And so the history of this is like, you had the rise and fall of the Roman Empire. Here you have the fall and rise of indistinguishability obfuscation. So we didn't have any constructions to 2013. In 2013, there was this breakthrough paper which gave like the first construction, but there was a bunch of attacks. And in fact, it was starting to look like maybe it wouldn't exist, or at least some prominent cryptographers, you can ask me who later, believed maybe it shouldn't exist. But there was this breakthrough work which constructed it under well-founded assumptions, which I won't tell you about. But if you want to, you can ask me about it later. So now we do believe that this exists, at least under long-standing crypto assumptions.
Yeah, but you can say who the authors are because they deserve credit.
Oh, okay, yes. This is there'll be a slide on this later, but this is Ayush Jain, Rachel Lin, Amit Sahai. And they also have a follow-up work to this in 2022, which removed one of the well-founded assumptions.
So if I understand right, you're building the I/O circuits from looking at the circuit C itself.
Yeah, it's an algorithm that takes as input this circuit and then gets to output another circuit.
But what if you just were given the outputs, not the circuit itself, but just
But like the truth table of it?
Yeah.
Yeah, good. So now you're saying, what's the functionality you want? Oh, okay, one thing I could do, one way to get an what is
I guess I just want to construct some circuit, some canonical circuit which matches the function.
Yeah, so if you hand me the truth table, one canonical circuit that computes the function would be just hand me back the truth table, right?
Right. But it's maybe too
big.
Too big.
Yeah, good. So then you have this question, which is if you hand me a truth table, can I produce a small circuit computing that truth table? And we believe that this problem is
Why do they? I mean, if you get the truth table, you get one polynomial time is the length of the.
But he wants to shrink it. Like, okay, if you're about to run in polynomial time, then you can just output the truth table. But if you want to output a smaller representation, we believe that problem's NPR. In fact,
That might be one way to construct.
Who will give a talk about this?
Yeah, well, actually, what you're saying, it turns out to be a very good intuition. Like, I won't tell you about how this thing is constructed. But the way that it's constructed is like a bootstrapping procedure where you say, okay, if there was some way where if I was given a circuit, I could come up with an obfuscation that just beats the truth table bound, like somehow, like slightly better. Instead of having a truth tables of size 2 to the n, if I can get something that has the I/O guarantees, but is of size 2 to the 1 minus epsilon times n, then you can bootstrap to obfuscation. That's actually how this construction works, although the later construction works a little bit differently. Yeah, there's like the slow XIO versus fast X. Okay, I won't get into it, but yes. Okay, good. So now what am I going to tell you next? I'm going to try and give you some examples of how to use I/O. We actually won't see the most powerful examples of how to use I/O because that would require us to know about PRFs and something else called puncturable PRFs, or PRFs are pseudo-random functions. Anyway, it would require some more background. So I'm going to give you kind of some of the easier applications of I/O, but hopefully it'll illustrate to you how to use this object a little bit. Okay, great. Good. All right. So the first application will be how to build one-way functions from I/O. In particular, there's this theorem that if P is not equal to NP, and here actually there's supposed to be an infinitely often, blah, 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 and a slash poly, but I told you I'm not going to include those things. And indistinguishability obfuscation exists, then a one-way function exists. In particular, the one-way function is the following. It'll take as input some string R, which we'll interpret as randomness. And what it's going to do is it's going to obfuscate the zero circuit. So this is just some circuit that always outputs zero. Although what we're going to do is we're going to add in a bunch of dummy gates so that it's of size like n squared. And then it's just going to obfuscate that circuit with the randomness R. Okay. Okay, so first is the definition of
The
F.
randomness is n bits? What's?
Yeah, good. I kind of suppressed this, but like, okay, this obfuscation algorithm, when it wants to obfuscate like a circuit of size n squared, it's going to maybe use poly n squared randomness. So this is actually going to be like a pi n, yeah. So it's like going to depend on what the randomness complexity of the IO algorithm is, yeah. But yeah, some polynomial. Okay, any
The
questions?
randomness would be longer than it's good.
Yeah, the randomness will be longer than n squared. Yeah, so n is not the length of R here. N is, yeah. Okay, is the definition of that function clear? Also, does everybody remember the definition of one-way function? It's like, this is a function where it's like, it should be hard to go from the circuit output from this back to R when I run this on a random R. Okay? All right, so here's the proof.
The IO itself was randomized, right?
Yeah, good. So the IO is a randomized algorithm, but secretly every randomized algorithm under the hood is just a deterministic algorithm.
Yeah, I know, with some seed, but like the point is, you
This is
said
the
this
seed.
is the seed.
This is the seed, yeah.
Yeah, okay. I forgot the role of R.
Yeah,
It's
sorry.
exactly the seed.
Good. Any other questions?
Yeah, is it clear that, so again, like we're not guaranteed that this is a one-to-one function, right? Like
Good, yeah, it's not necessarily, we're not guaranteed it's a one-to-one function.
So you're allowing me to give you
Any pre-image,
any seed that will give me the seed.
yep, exactly. Good, great questions. Any other questions? All right, so here's the proof. So the proof strategy is we're going to assume that IO exists, and there's some inverter for F. So this is some function which goes from like the circuit output back to some pre-image. And we're going to use that to show P equals NP. Okay, that's our strategy. And, for simplicity, actually, it's not so important for the proof, but like, just in case you haven't seen one-way functions before and you want to carry around less things, let's assume this inverter always works. It actually really works on average, but maybe that's more state to carry around. So here's the algorithm you're going to create for SAT. Okay. So I need to solve SAT, which means that I'm given some circuit C, and I need to tell, is it satisfiable or not? Here's what I'm going to do. I'm going to obfuscate C and then run the inverter on it, okay? The inverter is supposed to find me a pre-image to this obfuscated circuit under F, okay? If it actually did find me a pre-image under F, I'm going to say it's unsatisfiable. Otherwise, I'm going to say it's satisfied, okay? So this is the algorithm. I don't expect, we're going to go through the analysis in a second, but I want to make sure you guys understand what the algorithm is. So you take this circuit, you obfuscate it. Now, the things in the range of F are obfuscations of the zero circuit, right? So the obfuscation of C might not be in the range of this guy, but we're going to ask the inverter, hey, try and find me a pre-image under F, and either it will succeed and find a pre-image or it won't. If it succeeded, we're going to say it's unsat. Otherwise, we're going to say it's set. Okay. Any questions? Or algorithm makes sense. We'll do the analysis in a second. All right, correctness. So let's say this algorithm says unsatisfiable, or no is unsatisfiable. Well, what does that mean? It means that we found a pre-image under F, which means that when we obfuscated C, there existed some R such that when we ran F on that R, which gives you IO of 0 and squared R, that these two are equal to each other, right? So this is just the definition of inversion.
You said that functionally they are the same, so C on output 0.
Great. Yeah, exactly. So if this says no, we found this R, but since this preserves functionality, that means that's the zero circuit, which is the definition of being unset. Okay? Good. Make sense? Good. All right. Now the reverse direction, which is the harder direction, but not that hard. Oh, So let's say a circuit is unsatisfiable. Now we need to show that the algorithm says no. Well, if it's unsatisfiable, then the obfuscation of C is computationally indistinguishable from the obfuscation of the zero circuit because they're functionally equivalent. Now I claim that this means that the invert algorithm on IO of C should succeed with high probability. Why? Well, the invert algorithm works when I run it on the obfuscation of the zero circuit, because that's the definition of F. But the obfuscation of the zero circuit is computationally indistinguishable from the obfuscation of C. So if the inverter worked here, it should work here. And so then the inverter worked, so the algorithm says no. Okay. Hopefully, I mean, hopefully this argument isn't like too hard. It's like one of these things where you have to plug in the definitions and stuff like that. But hopefully if you understand it, then you'll have a good understanding of IO and at least a simple way of how to use it. Okay? Good. Any questions about this?
Why this takes 13 years?
Good. That's a great question. I think, ask me when we're not recorded. But it's like, it's one of those things where if you give me the theorem statement, I'm sure you'll be able to come up with the proof. But it's like, if you don't give me the theorem statement, like IO, I mean, it's a very strange notion, right? Like about functionally identical circuits, I don't know.
I think the point of the paper from 2001 that people remembered is that obfuscation does not exist.
Yeah.
That was like the message. And then these other things were viewed as, I don't know what.
Yeah. So it's like the people, they came up with this definition BBB. It was false, but as I said earlier, like no one believes, most people believe that that's like a contrived impossibility result. So they try to achieve other definitions and stuff like that. And it was not clear how to construct IO. It wasn't clear how to use it. I don't know how many people were thinking about that. But yeah, indeed, it is not too hard of an argument. Because you guys are mostly complexity theorists, I'm going to give you one more example. So both of these examples that I'm giving you, I'm avoiding the most powerful technique for using IO, which is this punctured PRF paradigm, which is a loss to you guys because that's like a really powerful tool. That's how you use it. But it has the advantage of, I don't have to explain that. So the second example I'm going to give actually hopefully will appeal to you guys because it's a statement in complexity theory. Also, it's one of my results. So,
Can I ask something about it?
Yeah, sure.
Before you move on?
Yeah.
Like, I'm trying to understand like the intuition behind why this would be a good notion.
Great.
And like here, you take a circuit that you know nothing about, and you obfuscate it.
Yeah.
And like supposedly, you want to say that, you can always obfuscate, say, the zero circuit or some circuit that you know everything about.
Yep, great.
Right, and so now, like, the idea is that you want to say that kind of if these two are indistinguishable and you can't know anything about the zero circuit, then you can't know anything. Like, is this what's supposed to be?
Yeah, so I think this is a good intuition. I mean, there's multiple intuitions you could have, but it's like what you're saying is like, I have this circuit which I don't know anything about, but IO gives me this property that like makes functional equivalence. Like if two things are functionally equivalent, I'll get the same property. So if it was functionally equivalent to the circuit which I know I have in hand and which I can use to build this one-way function, then it lets me transfer information about circuits who I know completely their functionality to circuits who maybe I didn't know its functionality a priori. I mean, it's a really, even though at first it's a kind of strange notion, it's kind of actually a very beautiful notion, maybe. And like, I don't know, there should be definitions like this new definitions that have this flavor. I think that'll be useful in complexity theory. Maybe it won't be useful in cryptography because it'll have something to do with like the polynomial hierarchy or something like that. But I feel like there's more definitions of this flavor that should be powerful elsewhere in complexity theory. Okay, great. All right, so let me tell you about the second application, and then after I tell you about the second application, we'll break, and then we'll go into the wheelbarrow results. Okay, the second application is about hardness of range avoidance. So I guess Ilya mentioned range avoidance, was it last week? Anyway, some time ago. It's this problem which was introduced by Kleinberg, Korten, Mitropolsky, and Papadimitriou. It says, given a circuit C that maps n bits to n squared bits, so it's a circuit that stretches, find me some string outside the range of C. Okay? So because this is a stretching circuit, there always must exist something outside the range of C, but now I want you to find it. Okay, so we have a problem. The first thing you can ask is, okay, how hard is it to solve this? So who can give me an algorithm for this problem? Hanlin? I guess you have many algorithms for this problem. Good. So one thing you...
Sampling, yeah, okay.
Great.
Some element in the sampling.
So here's a really fast randomized algorithm. It's actually crazy fast because you don't even have to look at the input. You just need to know what its codomain is. Just output a random string. And that'll work except with probability, except for exponentially small probability. But a question that people were interested in, and they were interested in for a bunch of different reasons, which I won't tell you about, was, is there a fast deterministic algorithm for this problem? And here's a quote from a paper with Hanlin where it wasn't clear whether or not there was a deterministic algorithm, but it turns out you can use I/O plus complexity theory in order to show that there's no deterministic algorithm, no fast deterministic algorithm. And I'm going to tell you about this proof because hopefully it'll also illustrate a little bit about how you use I/O. Okay, so here's the proof. So what's the proof strategy? We're going to assume that there's I/O and assume that there's a deterministic range avoidance algorithm. Our goal is to show NP equal to co-NP. And reminder, NP equal to co-NP, my goal is to certify that some circuit is unsatisfiable. And so here is our strategy. This is going to be our certificate of unsatisfiability. We're going to prove the following equivalence. An input circuit is unsatisfiable if and only if the following condition holds. Ignore this part, I should have, yeah. The condition is that there's going to exist some string y and exist some string r with the following guarantee. The guarantee will be that when you run the deterministic range avoidance algorithm on the obfuscation of some circuit, which I haven't told you about yet, but will depend on C and Y, with randomness R, you get back Y. Okay, so I haven't told you what the circuit D is, but basically you're going to run a void on some obfuscated circuit, and you're going to check whether or not you got back Y. All right. Next I'm going to tell you what D is, but hopefully everything makes sense up to here.
Yeah, even that I'm still a bit confused.
Okay, yes, yeah.
It's only a certificate, so I don't need to generate Y and R myself. I'm giving that.
Yeah, good. So when you show NP equal to co-NP, you don't have to come up with the certificate quickly. You just need that its certificate exists.
Yeah.
So if I need some short certificate for this, and the certificate will be I'll hand you Y, I'll hand you R, and then you can run this part yourself because this runs in polynomial time, that runs in polynomial time. This construction is also in polynomial. Good. Yeah. Perfect. Maya, you look like
Avoid is,
oh.
you can't control which string Y avoid returns, right?
No, avoid is just some our goal is to show there's no deterministic range avoidance algorithm. So it's just so when we're working here, we just assume that God comes down and hands us some algorithm. We have no control over what it does. And we're saying on this condition is that that algorithm that God hands us down on this input outputs Y. But we have no control over what it does. Yeah. But was that your question? Or?
It just seems like avoid has so many degrees of freedom that you could do something evil, always have it return Y prime. But I'm sure I'll see the proof completely.
Yeah.
Oh, that was my intuition.
Okay, so I need to tell you what the circuit D is. So the circuit D is going to be parameterized by the choice of C and Y. And what is it going to do? It's going to take as input X. It's going to run C on it. If C outputs 0, it's going to output the all 0 string. If C evaluated to 1, it's going to output the Y string. Okay, and kind of the important properties about this circuit D is that when C is unsatisfiable, you only hit this top condition, you only output all zeros. But if it was satisfiable somewhere, you're going to get this Y hit it. You're going to hit this Y. And that will come up in the proof. Okay. All right. So does the proof strategy make sense? And next we're going to prove this equivalence. But our proof strategy was to show that these conditions imply NP equal to co-NP. This is going to be our certificate of unsatisfiability. Now what do I need to show you? I need to show you that if it's unsatisfiable, then there exists such a Y in R. And then I need to show you if there exists such a Y in R, it's unsatisfiable.
Okay, at least we can see how Maya's remark is solved by this, right? Because the obfuscation is like...
Yeah, good. Yeah, exactly. The obfuscation is going to kind of hide. You might think this avoid algorithm will be like, you want this Y? I'm going to look at this, and then I'm going to do the Y prime. But because of the obfuscation thing, obfuscation is up to me. All right, good. Proof in the reverse direction. So what do I want to show? I want to show that if this condition holds, then the thing is unsatisfiable. Hopefully this isn't too hard to see. If we had such an R and a Y, well then, by the correctness of the range avoidance algorithm, we know that Y is not in the range of this circuit. By the perfect functionality of I/O, now we know that Y is not in the range of this circuit, which I've written down back here. And then by the definition of this circuit must be unsatisfiable. Because if Y is not in the range of this circuit, that means you must have never hit this condition, which means the circuit was never satisfiable. Okay, good. So that's the reverse direction. Everybody good? Like it? Nice? Nice. All right, forward direction. This one will be the harder direction, although hopefully not too hard. And this is where we'll see the answer to Maya's question and the usefulness of I/O. So our goal is to say that, if you hand me an unsatisfiable circuit, there exists such a Y. So let's fix that circuit C. And now I claim that there must be a Y star in 0, 1 to the n squared with the following property. When you run the avoid algorithm on I/O of D, and now before I was putting Y here, but now I'm just going to set this to the all one string. Again, yeah. And I'm saying when you run the avoid algorithm, it must output Y star with probability at least 2 to the minus n squared. Why is that? Well, this avoid algorithm on this distribution from here to here needs to output something. And so I'm just saying there must be at least one string it outputs with probability at least 2 to the minus n squared, just by averaging argument. Okay, good. Everybody believes that? No, Max, you seem... Okay, good.
I'm not sure what you're going to do with it.
Oh, what I'm going to do with it. Okay, good. Great. So we have this Y star, which we get just by an averaging argument. Now, since C is unsatisfiable, note that the circuit D you get when I put all ones here is functionally equivalent to the one where I put Y star here, right? Because C is unsatisfiable, this condition never triggers, so these two circuits are functional.
It would be natural to write this first because for every Y and Y prime, this is correct because the circuit is just the all zeros.
Yeah, fair. Good. And this, as you point out, these two conditions hold, this condition holds no matter what two strings you put. Okay? So now what I will claim is that I/O security will give this. If we look at the probability that the event that happened here happens, but when I replace 1 to the n squared with Y star, well, how much can change? Okay? Well, the event when we put 1 to the n squared here happened with 2 to the minus n squared probability. Now when I change this to Y star, I/O security will say, hey, if that event happened over there with 2 to the minus n squared probability, it's going to happen here with 2 to the minus n squared probability with some security loss associated with the I/O. I said the I/O was like this should be minus. There should be a minus sign there. I/O is sub-exponentially secure, so you really don't get any security loss if you set lambda to be a sufficiently large polynomial, which you can do, and then that's greater than 0, which will give us our existence, which is the next line. But did this switch make sense? You have some event that occurred with noticeable probability, or depends how you define noticeable, with some probability over here. The probability that event happens when we switch from the 1 to the n squared to the Y star should be roughly the same, just because we didn't change functionality at all.
Oh, also want to remark that this is the place you use avoid has a polytype always.
Good. Yeah. This event, you need to be able to check it in like efficiently in order for the indistinguishability to work nicely. This is also, so it's important that avoidance is running in polynomial time. Okay, and if this probability is greater than 0, then surely there exists some R and Y such that the event.
This is the only place you use deterministic?
Good. So deterministic is used. Deterministic is used actually on the other slide too. Sorry. Here, when I went from or the correctness of the avoid algorithm, because it's deterministic, you know that this condition hits. Or you know, if this avoid algorithm was randomized, right?
Yeah.
Then there was some, and okay, there's some other randomness, maybe we'll say S here, right? And if I handed you some Y, R, and S such this happened, you don't know that Y is not in the range of this. For sure. Because S could have been bad randomness. Okay. So it's used here. Okay. Another way to say this is what are we using about a deterministic avoid algorithm that wouldn't hold for a randomized algorithm? It's that if I run a deterministic avoid algorithm on a circuit and it outputs some Y, that's a certificate that Y is not in the range of the circuit. Whereas if you have a randomized algorithm, for example, the algorithm that just outputs a random string, it doesn't certify that the string is outside the range of the circuit. And and the assumption we're using NP versus co-NP is something about certification. So fits in, but yeah. All right, great. Oh, okay, nice. We're at exactly the hour mark. Good. Okay, so did that argument hopefully make sense? So hopefully you should believe that there is no deterministic range avoidance algorithm. Hopefully it tells you something about using IO, although most of the powerful IO algorithms actually don't, or IO arguments don't look quite like this, but they have some flavor of this. And one of my goals was to say, indistinguishability obfuscation, you can use it to attack your problems. For me, it's been really powerful. So this is like one example of a bunch of things that I've done with a bunch of people, including Hunlin, that answers questions in complexity theory or outside of cryptography using IO. So hopefully might be useful to you too. And the last thing I want to say before we break, I want to come back to Dickens. So, Dickens' Tale of Two Cities, he starts off famously, the worst of times, it was the best of times. And I said, in some sense, IO is not the right definition. In some other sense, it is like the best possible definition. What do I mean by this? I'm not going to give you a formal proof, but I'm going to give you kind of a sketch of the proof. Let's say you had a different obfuscation algorithm, your favorite obfuscator. Maybe it has some really nice properties, right? And you're like, this is great. It would be, IO is okay, but I have my obfuscation star. It has some really great properties. I'm going to argue that actually IO will pretty much have those properties too. Why? Well, okay, you have your favorite obf star. You could run that on a circuit. Well, what I could do is after I ran obfuscation star, I could run my IO algorithm on it, right? And I claim this is only more obfuscated than what I had before, right? Because if I had something that was kind of obfuscated, there's nothing that I should be able to do in polynomial time to make that like less obfuscated. Because the definition of the obfuscation algorithm is that in polynomial time, you can't really quite do anything. So, okay, take it on faith. After you IO this, you should not be able to undo obfuscation. Well, I claim this is computationally indistinguishable from just skipping obfuscation star, and just running IO on C with some extra dummy beads. Why? Well, obfuscation star blew up the size of C by something. Well, I could just match the size over here. And now these two circuits should be computationally indistinguishable because they're functionally equivalent and they have the same size.
This is assuming that obf star is like at least functionally
good. Yeah. So the properties you need out of obf star is that it runs in polynomial time and it has perfect functionality, which seems reasonable. So in this sense, it turns out that a wide class of properties, pretty much every property you would want, IO, which seems like obviously not the right definition, is like a best possible definition, which is actually very strange. Like, and in fact, like the cryptographer, it's weird because we have a construction of IO, but we don't know how to construct a bunch of other things stronger than IO, which we think should exist. So like we have the algorithm. I mean, I guess this happens a lot. Like we know if P equals NP, we know what the algorithm is. I don't know, it's strange. So yeah, all right. So that's what I wanted to do in the first half. Next, we're gonna bring the wheelbarrow.
So that definition is like the universal property of IO?
That definition. Which definition? The best possible?
No, I mean the definition of IO.
Yeah, the definition of IO is
It's like the universal property of IO.
yeah. Or I don't know what you mean by universal property, but it's like any other definition you would make where, okay, the security properties you want are like falsifiable in some sense, you'll get them from IO. Yeah. Yeah. So I don't know, yeah. And somehow this best possibleness, like usually when you get a best possibleness, for example, like we know the algorithm for P equals NP if it exists, it's not a very useful algorithm. Like it was somehow that doesn't, there's no argument, there's not interesting technical arguments that use that fact to do something. I mean, maybe there are, but like somehow from IO, like it being best possible actually turns out to be pretty useful. And maybe some interpretation of what's happening with the wheelbarrow next is that like somehow we can exploit this best possibleness. All right, okay, well, there we go. All right, thank you. We'll take a break first. I don't know. Okay, good. So it turns out if you have a weakened notion of functionality, like for most weakened notions of functionality, you can upgrade it to perfect functionality under like de-randomization type assumptions. Like, so for example, if it holds on like half of all inputs, where half, but the individual on every input, it's like has like a coin flip or something like that. Yeah, I mean, perfect functionality is important to the argument, but to the avoid argument, but it turns out there's like cryptographic tricks you can do to upgrade most approximate functionality to perfect functionality in most cases.
I asked because this question of looks a lot like the question of learning from data, like learning a circuit from data. So if you're given just a bunch of values,
yeah,
can you reconstruct a circuit which has the required properties?
I see. And you're saying then might only get approximate functionality.
And we do sort of know in practice how to learn from data.
Yeah. So it turns out like these types of approaches, you can show likely or not, you are unlikely to give you IO because like if let's say you just learn from data, then what'll happen is you'll get like a statistically secure obfuscator where it's like, because if I just, use input output examples on the circuit, I don't use any other property about it, then like the output of the IO is going to be statistically close to each other based on, and such things like, it turns out if they exist, the polynomial hierarchy collapses or something bad happens. But although there is some people are investigating whether that approach is possible for weaker circuit classes, so it is interesting. But all right, good. So now I'm going to tell you why obfuscation IO is a wheelbarrow. Okay, and I want to start by like motivating it with some phenomena, telling you about this phenomena which I hinted at earlier, which is like the unreasonable effectiveness of IO.
Where's the picture of Wigna?
Oh, right. Yeah, I should have a picture of him. Yeah, you're right. Good. I have a different picture instead. Okay. So the unreasonable effectiveness of IO, and it's basically this. Oh, right. I'm going to violate my apologies. There's going to be some acronyms here. But you don't need to know them. Good. Maya's on a quest to kill acronyms. So, yeah. Anyway.
Specifically.
Yeah. So the unreasonable effectiveness, it's basically if you assume IO plus P not equal to NP, you get a whole bunch of primitives in cryptography. This was kind of this crypto completeness. You get one-way functions, we saw this, but you also get like public key encryptions, non-interactive zero knowledge, functional encryption. It seems like you get almost everything you want in crypto. If you just make these two assumptions, it's like super effective. You just make IO plus this like minimal complexity assumption, P not equal to NP, you get pretty much everything you want, which is great. Now, let me ask you, does this smell like anything that we've seen before in complexity? What does this remind you of? What does this remind you of that, we teach in our undergrad courses? You know, there's this IO plus P not equal to NP. It seems like you get everything you want. Max, what do you think? No.
I'm lost.
You're lost. Yeah, somehow it's like you make this one assumption and then you get almost everything you want.
One-way function.
Good. One-way functions is another good example, yes. But let's say in complexity theory. You make one assumption, you get false. What? You said false? False. Oh, that's a good one. Yeah, I think that might secretly be what's happening in some of my papers, although hopefully not. Good. Okay. So I claim this is like maybe a picture we've seen before. The unreasonable effectiveness of P not equal to N, right? So an empirical phenomena, or maybe it's not an empirical phenomenon, or at the very least it's an empirical phenomenon, is that if you assume P not equal to NP, then it turns out that like all of these natural problems, like circuit satisfiability, maybe that's not natural, but like clique, integer linear programming, traveling salesman, you throw a dartboard at the wall, you interpret it as a problem, probably you can show that that's not. So if you just make this assumption that P is not equal to NP, and stat is hard, then we get all this great stuff.
But this is different because they are all equivalent.
They're all equivalent. Yeah, maybe. Okay. Maybe. All right, we'll come back.
I couldn't take it.
Yeah. Well, okay. These things are equivalent, assuming P not equal to, or assuming IO exists. If IO exists, then you can show these are equivalent. Anyway, okay, we'll come back.
The one-way function is not equivalent to PKE.
If IO exists, it
Okay.
is.
Okay, I see.
So there is some sense in which they're also equivalent too. Anyway, okay, so that's kind of interesting. I don't know. We'll come back to this. This is some foreshadowing. All right. But anyway, there's this unreasonable effectiveness of IO, and it seems like you can get everything from IO. And from what I understand is like, IO came out in 2013. There was these constructions, and then there's these flurry of results, which are like, okay, we can get this, we can get that, we can get this. And then apparently there were some like discussions on PCs where they were like, okay, guys, you can get so much from IO, we can't accept everything, is what I heard. So it seems like you can get everything, but actually I want to argue, or I guess I won't argue because you're not cryptographers. I will tell you that there's some things missing from this picture. Okay, so what's missing from this picture?
A picture.
Oh, yeah, good. The one thing that's missing is the picture, and I guess this isn't a picture either. The one thing that we don't know how to argue about is like optimal security. Okay, so these are one-way functions, PRGs, and public key encryption. Usually, in theoretical cryptography, we say that scheme is secure if there is no polynomial time algorithm that breaks it. Sometimes you go further than that. You say it's secure if there's no sub-exponential time algorithm that breaks it. But you could try and go further than that, right? You could hope for better security. And in fact, in practice, this is what they do. I think like when they build AES, which is what you'd use to encrypt the messages you send to the bank online, they actually believe that the best attack, I think, is like 126.8, 2 to the 126.8, whatever that means, has security. And practitioners want that because that's exactly, it'll make their scheme more efficient. So let's say we want some scheme that is secure up to naive attacks. So like, for instance, you might want a one-way function family where there's kind of a naive attack, which says if I try, one way to invert a one-way function is just try random points. So if I spend t time, I might have t over 2 to the n6 extra. This, I just try random output, try random inputs to the one-way function and see whether or not I actually hit the thing. And you could hope to try and construct a one-way function family such that this is actually optimal. And this is something that's kind of difficult to argue about, usually in theoretical cryptography, because the assumptions used, things like LWE or discrete log or stuff like that, if you know what they mean, they're actually they don't have optimal security. They're actually non-trivial attacks on can beat them some exponential time. So it seems kind of hard to argue about optimal security. And I'll make this note here, if anyone here is an expert, Okay, but maybe not. All right, if there's some distinction here between families and fixed one-way functions, there are these like, but maybe I won't make this comment. Okay, so this is one thing that's missing. We don't know how to argue, we don't know how to construct schemes with optimal security. Another thing that's missing is one-way product functions. So this is something else about the hardness of one-way functions. What is this? Let's say I have a one-way function f, and I want to argue about how hard it is to break the one-way function on multiple different inputs. So let's say there's y1 up to yk, and I want to break all of them simultaneously. Okay, so you expect kind of like a multiplicative growth for each y you add here. So like in the extreme case, you'd expect like a polynomial time algorithm to have like success probability like 2 to the minus nk, right? Like, so it has like 2 to the minus n shot for each one of these and then multiplies together to 2 to the minus n. Okay, and this is like, you know, a really powerful thing. This is like less than 2 to the n. This is like a very small number. And that makes it very difficult to argue about this. And in fact, there's like these classical barrier results that said, oh, you can't argue about this using black box techniques, and there's actually one-way functions you can construct for which this phenomenon doesn't hold. Okay, I guess we're complexity theorists, so maybe, you know, this was just something that we didn't know how to construct, and it seemed difficult to argue about things less than 2 to the minus n. And it turns out it has some important applications. Holmgren and Lombardi have some thing about this, but I won't talk about this. But mostly what I want to tell you is that, like, it turns out there's a whole bunch of things missing. And so if you know what these things are, then great, like lossy functions, correlation intractable, non-intractable responsiveness, even simple things like collision resistant hash functions, they're kind of like, they don't have a good theory in IO. Like we don't know how to build them from IO in nice ways. And there's a lot missing from this theory. Okay?
And again, like when you say missing, you just mean that we cannot deduce the existence of these things out of purely IO plus P is not equal.
Or any assumptions is unnatural.
Yeah, and from any natural assumption. Well, it depends on, for at least
You
the
can
first
assume
two
that you can just assume that they exist.
Yeah.
Which is a natural assumption or not.
Not so natural.
Yeah.
Not so natural.
Yeah, so for the first two, the two that I highlighted, we didn't know how to construct them from any nice assumption, where nice is some sociological
Yeah.
At least you needed like a candidate hard function right now, like for the.
Good. And so you need at least a candidate hard function. Okay, good. That's some good foreshadowing. All right. So now let me tell you about our results at a high level. And our results are very simple, or simple to state in some sense. It is wheelbarrow plus brick equals house. Okay? Wheelbarrow plus brick equals house. Okay? So wheelbarrow here is going to be IO. This is a really good wheelbarrow. It's sub-exponentially secure. And whenever I say IO, I'll assume it's sub-exponentially secure. And then brick is going to be a complexity assumption, something like P not equal to NP, NP not equal to co-NP, or maybe strengthenings of that, quantitative strengthening of that. And then house is going to be cryptographic. Okay? And it turns out, like, our results will be able to say that, like, if you have IO plus some appropriate complexity assumption, which might involve, at the very least, having some function which has that hardness, then you turns out a whole bunch of stuff. You know, okay, I don't really care. You know, for this stuff, if you know what they are, great. But in particular, you can get like optimal one-way functions, optimal PRGs, optimal public key encryption, one-way product functions, and some other stuff. But again, my focus is not to really tell you how to construct these things. I want to focus on what the phenomenon is here and give you a flavor of what proofs look like. Okay?
Rahul, could you say for one-way product functions, is there any candidate for that or already, just even unrelated to IO or no?
Well, I mean, I guess you could just conjecture maybe AES is like a one-way product function. Yeah. Okay, good. And you know, wheelbarrow plus brick equals house. This is a very powerful recipe. You know, I think you know, building housing is important, and you know, here in Princeton, I feel like it's important to point this out.
You shouldn't show us any of the institute.
Oh, this thing?
This is what prevented the construction of, for example, faculty housing for 20 years.
Oh, really? Oh, okay, but
Oh,
okay, but you'll see. So I encourage us all not to do this, but to be YIMBYs. Who knows what YIMBYs are?
Yes, in my backyard.
Yes, in my backyard, although in this case, so okay, there's the NIMBY movement, which is no in my backyard, which I guess prevented faculty housing here. Yes, in my backyard says, okay, let's build it, but actually in this case, it's different. Yes, IO makes.
Cryptography.
Yeah, I don't know. I had a nice thing going. I couldn't really figure out what to do here, but I guess we don't like acronyms here, so yeah. Anyway, okay, good. All right, so let me tell you about this approach in a little bit more detail. So the approach is going to be as follows. We want to show that some cryptographic primitive Q exists. For example, one-way product function. What are we going to do? We're going to use IO to show that that thing exists, assuming some problem pi sub q is worst case hard. So now, here you're in complexity world, cryptography world, but now some problem being worst case hard, that's more complexity world. And in fact, for example, this pi sub q is usually going to be kind of the natural worst case problem you'd associate with q. So if this was one-way functions, well, one-way functions say something's hard to invert on average. What's a worst case version of one-way of inverting on average? Well, one thing is SAT. SAT is asking, can you find me a pre-image of 1 in your circuit? So then the pi sub q here for one-way functions will be SAT, and for one-way product functions will be some direct product version of SAT, or SAT on multiple instances. And so now you have this reduction, or you can reduce the existence of a crypto primitive to the worst case hardness of some problem. And then hopefully you can use complexity theory to say, okay, some hopefully standard complexity assumption, maybe NP not equal to co-NP or something like that. We'll show you that this problem is worst case. Okay, this is the schema.
but none of these EGs.
These EGs will be a theorem.
These EGs will be a theorem.
Or these particular EGs will be a theorem.
Okay.
Although I won't state it formally, but yeah, we'll see a chart. Well, I promised you 3 different columns, so we'll see.
Okay.
These foreshadowing. You'll see 3 different columns later. Okay, yeah. Does that answer your question or something? Yeah. Okay, good. And I want to say that actually this phenomenon was kind of implicit previously. I guess we saw this one-way function reduced using IO to SAT not being in P, and exist public key encryption also reduced to SAT being in P. And there's even this work which showed that there are maybe I won't tell you what this thing is because then I have to tell you what timeline puzzles is. But there are some existing examples where this kind of phenomenon was implicit. Good. And now I want to come back to Wigner, which is, remember we had these 2 pictures, right? The unreasonable effectiveness of IO and the unreasonable effectiveness of P not equal to NP. What I want to argue is that, hey guys, they're the same picture, okay? Why? Well, if you accept this phenomenon, which maybe you don't, but let's say you did, that we take a crypto primitive Q, and then you can use IO to reduce it to the worst case hardness of a problem. Well, what is the lesson from P not equal to NP? It's like saying if you have a hard problem, most of the time, it reduces to P not equal to NP. So if you believe this, when you use IO, you can take Q, transfer it to pi sub Q, and most of the time, you'll be able to base that on P not equal to NP. So there's some heuristic philosophical explanation for why is IO plus P not equal to NP so powerful? It's the same reason why NP completeness is so powerful. Okay, great. Now, any questions? All right, so now let me tell you about the paper in 3 columns. Famous 3 columns. Right. So what I'm going to do is I'm going to put a crypto primitive Q here. Some of them you might not know, which is, I'll just flash it up there, but if you know them, great. And then I'm going to tell you what the corresponding worst case pi sub Q is. And I'm going to tell you what we know about its related complexity class. So the first one-way functions. It turns out you can use some IO machinery, actually it's IO machinery I haven't told you about, it's this like punctured PRF paradigm, which I won't tell you about, to reduce this to unique search SAT. So unique search SAT is like, I give you a circuit which has exactly one satisfying assignment. And then you can use that using classical complexity techniques, which I won't tell you about, with P not equal to N. Now you might ask, wait, Rahul, why are we doing this? We already saw a way to get from one-way functions to P not equal to NP and had nothing to do with unique search SAT. It turns out that we want these arrows to be fine-grained. And what I showed you before is not fine-grained. I'll explain this in later slides, but what we want is these arrows to be fine-grained so that if we can assume kind of like maximal hardness of this, then we can, our optimal hardness of this, we can get optimal hardness of this. And optimal hardness of P not equal to NP says, oh, if you want to solve SAT, you need roughly 2 to the n time. Okay? Then you can go to other primitives like PRGs and like public key encryption. And then, maybe kind of naturally, the right problem you'll turn into is like unique SAT, the decision version of SAT instead of the search version of SAT. So for one-way functions, like the goal was to find a pre-image. So it's kind of some search problem. For PRGs, you want to distinguish random from pseudo-random. So it's a distinguishing problem. So you expect a distinguishing problem over here. This is also using some punctured PRF things. And then actually you run into some issues when you try and do fine-grained complexity. It turns out maybe while you are trying to get a fine-grained reduction, maybe you expect P not equal to NP here, but the best we can do is NP not equal to NP here. And it turns out we'll have some interesting complexity theory that I'm going to tell you about. And yeah, you can repeat this for a whole bunch of stuff. Maybe I won't tell you too much about this.
So you were suppressing a lot of things. So the top row P not equal to NP is actually
yeah.
Okay.
Yeah.
And how about for the second and third lines?
Yeah. So these are all fine-grained. So if you assume, okay, this one's also fine-grained. So if you assume maximum, the hardness you get here is going to match the security you get here. This one is a little bit like the exact hardness trade-off versus optimality here is like a little bit more complex, but like if you assume optimal here, you will get optimal there.
What is optimal hardness for NP versus core NP?
It's saying if I want to have a non-deterministic circuit for unsat, it needs to be of size 2 to the n.
For MA protocols, this is false.
Deterministic circuit.
Although like generalizing MA into NP/poly is quite overhead. Okay, that's.
Oh, okay, interesting. Yeah. Okay, good. All right, and it turns out that there are some other cryptographic primitives where you can also do this reduction. You'll get some pi sub q, but actually we have missing complexity theory. I don't know how to connect those to.
But your result is meaningful for whatever complexity you get on the assumption, right?
Yeah.
It doesn't have to be 2 to the n maximally hard.
Yeah.
Okay.
Yeah. I didn't want to. Yeah. Okay, and then anybody know what YFP is?
Your favorite problem.
Great, yeah, Ilya Vukovic. Yeah. So, yeah, be great to add more problems to this list. Okay, so now I want to tell you about, or actually now I have an intro. Okay, intro perspective. Okay, so now we've seen some technical stuff, so I want to tell you some philosophical stuff. So who is this guy? Leibniz. Good. So he is Leibniz, but he's also something else that I foreshadowed.
You said it's Hardness great grandfather.
Yeah, good. Wow, nice. Yeah, why is that? So you could make this line of advisor to advisee. You go from Leibniz, Bernoulli, Euler, Lagrange, Poisson, Dirichlet, Lipschitz, Klein, Story, Lefschetz, Minsky, Blum, and from Blum, I think you go to Sipser, you go to Rahul, other Rahul, and then you go to Hanlon.
But you missed some greats.
Would miss some what?
Great.
Oh, yeah. I had to, I should have put a great ... But so one thing that Leibniz did was this like philosophical principle about if two things have the same attributes, then they must be the same. Another thing that he did was conservation of energy. Oh, I should say that this one's actually contested. I can tell you about the story about that later, but this connection, there's some debate about. Whatever, I guess from high school, this is burned into my head, like energy is not created nor destroyed, only transferred. And at least one perspective I have in IO, I'm just trying to burn this into your brain any way I can, is that like IO doesn't create or destroy hardness, right? Like it's a way of transferring hardness. You get the hardness of P not equal to NP, and you can transfer that into building one-way functions and public key encryption, something like that. Another like thing is like, we know if P equals NP, then IO exists, but you can't do anything with it. So if you have a wheelbarrow, but you don't have any bricks, it's pretty, not very useful. Okay, great. So now I'm going to tell you about some of the complexity theory that was on those columns. Okay? In particular, I'm going to tell you some of the ideas between going from optimal hardness of NP into optimal one-way. Okay. So let's start with this question, which is like, how hard is NP? And here maybe I'll have to say a little bit more complexity theory than I included on my crash course, but hopefully it won't be too bad. So let's say you have a non-deterministic algorithm. A non-deterministic algorithm has two resources. One is non-determinism, which is like how much guessing it does. Another is like how much time it does, which is how much time it uses when it doesn't guess. If this first top part of the slide doesn't make sense to you, it's fine. We'll reduce to a part that's something that will make sense to you later. You could ask, if I have a non-deterministic algorithm, what's the best deterministic algorithm I could get for that problem? Well, one thing you could do is you could brute force over all potential guesses. That'll cost you a 2 to the W. And then then run in poly-T. And as far as I know, and as far as Ryan knows, this is the best we know how to do. If you have an NP problem, this the best way to turn it into a deterministic one is this 2 to the W times poly-T. If you can improve upon this significantly, then you can get some breakthrough circuit lower bounds. And you could ask, or maybe even conjecture, whether this is optimal. And it turns out this is equivalent up to like some poly-T factors into asking whether for the circuit SAT problem is 2 to the n times poly-T necessary. Okay, good. And so then the theorem we get for one-way functions is that if you assume there's sub-exponentially secure IO, and you assume that algorithm is optimal, I'll call that optimal hardness for NP, then you will get an optimal one-way function in the sense that if you spend T time, then the best success probability is poly-T over 2 to the n.
Why is it poly-T instead of T times poly-n?
Oh, yeah, maybe it should be, well, okay, there'll be some extra blow. Maybe it should be poly-T comma n, if that's what you want. Because they're saying exists optimal function, I'm saying your success probability is at most this. So I'm going to lose some factors in the reduction, right? You're saying you want like a proper T?
Yeah, like linear in T.
Yeah.
That's truly optimal.
Yeah, I guess that's truly optimal. Yeah, we don't get that much. I think yeah, okay, we can talk about it. Okay, so I'm going to tell you, we'll be able to go through at least one of the kind of beginner steps in doing this thing, because it won't use too much crypto background. So the warm-up is going to be trying to get some sort of fine-grained worst case. Fine-grained worst case to average case reduction for SAT. So what do I mean by this? What I want is some distribution I can sample from. Sample means that there is some like polynomial time algorithm. When I plug in randomness, it spits out a sample from the distribution, which will spit out a circuit and a satisfying assignment. And I want that finding a satisfying assignment for C is as hard as a worst case instance. So I've sampled this from a distribution, but I want this to be as hard as a worst case instance. In particular, I want finding a satisfying assignment for C, which is going to be a circuit of on n inputs of poly S size, is at least as hard as finding a worst case SAT instance satisfying of n inputs at S size. So if I have a fast algorithm over here, I can transfer it to a worst case algorithm over here. Okay, does this make sense? Or the question make sense? Like, this is what I want. I want to come up with some distribution on SAT instances that is as hard as the worst case. Okay, and I'm going to tell you how to do this using IO. All right. So the attempt, okay, what is the first attempt at this? A first attempt at this actually is to use the ideas from this proof we saw earlier, which showed how to go from a p not equal to np in IO in order to get one-way functions. And how did that work? It kind of said, okay, what I'm going to do is I'm going to sample a random witness, which you should think of as kind of randomness to the IO algorithm. Then I'm going to obfuscate the zero circuit to get some circuit, obfuscated circuit B. And now what is going to be my search set instance? I'm going to say, hey, find an X such that B is the obfuscation of 0 with randomness X. And it turns out you could try and do this, but it turns out you'll run into some fine-grained issues here. It's kind of like what'll happen is like, okay, how hard is it to find this X? It's like related to like, what is the randomness complexity of this IO and its security? And you're going to run into some issues. If you can see it, great. If you don't see it, then you can believe me. It turns out you'll want to actually use a different construction. Okay, good. Does anybody have any ideas as to what maybe you could do instead? Like somehow like the problem with the problem with this is that like the way we were using IO is like we wanted to say that like this circuit C, you know, if you could find a satisfying assignment to this, then I can find a you know, solve SAT on the worst case. But the difficulty is that like this depended on like what the randomness complexity was here, because that's going to be the input length to C. Like we don't want to have the input to this be the randomness of the IO algorithm, because the randomness of the IO algorithm could have like an arbitrary poly blowup, and that's going to kill our like the fine-grained optimality of our thing.
Can put the PRG inside.
Yeah. Why don't
You could put a PRG inside, but now what's like, how optimal is that? Now you need that PRG to have optimal hardness. So, and so then it seems difficult, although that is a good intuition, because it turns out once you have an optimal PRG, you can pretty much get any optimal other crypto.
Sorry, this is like to deal with the problem that the randomness blows up.
Yeah, the randomness blows up, so then the circuit, Okay, so then what you'll actually do is a slightly different approach, which is kind of obfuscate a point function. What you're going to do is you're still going to sample this random W, but now it's going to be n bits. But now you're going to obfuscate the circuit, which maps X to 1 if and only if X equals W. So this is a circuit which only outputs 1 on one point, W, and is 0 everywhere else. And I'm going to claim that this circuit C is going to be as hard as a worst case instance of circuit, up to 0. Okay? And kind of the point, one of the nice points here is that like now the input length here is decoupled from the randomness complexity of this. And the other thing it's decoupled from is the security parameter of the obfuscation scheme. So I can set that security parameter to be arbitrarily as large as I want, and it'll blow up the size of C, but it doesn't blow up the input length to this circuit. Okay, good. And what we're going to do is we're going to try and say that if you had some solver that worked on this distribution, I want to create now a solver that works on worst case search set instances. And the way we're going to do it is using this two-part approach. Okay, we're going to say take this worst case or average case solver on this distribution. We're going to turn it into a worst case solver for search unique set. Search unique set is again, where you want to find a satisfying assignment and you promise that there's exactly one. And then it turns out you can use some complexity theory, which I won't tell you about, to turn that into a worst case search set solver without the uniqueness guarantee. Okay, so I'm going to tell you about this implication. Oh, that's value, that's wrong. Yeah. Okay, good. So how is this going to work? So I'm going to start by assuming I have an average case solver for D. Now I need to create a worst case solver for search unique set. And so in this algorithm, I'm given a circuit C, and I need to determine whether it's satisfiable or not.
You have the promise that it says everything.
Good, yeah. And this is an instance of search unique set, so it has exactly one satisfying assignment. So we're going to do two things, okay? And the first thing that we're going to do is we're going to re-randomize C, and this is going to use that it has exactly one satisfying assignment. And then we're going to do something called solve and unshift, okay? These are going to be the two steps. So what I'm going to do is I'm going to take my worst case instance C, I'm going to convert it into kind of an obfuscated shifted instance C tilde. How am I going to do that? I'm going to sample a random shift Z in 0, 1 to the n. And I'm consider a new circuit that maps X to C of X XORed with Z. Okay? So basically, if C had a satisfying assignment here, I'm going to like shift it by Z. Okay? So remember, C only has one satisfying assignment, so we just move that one place where it is. Okay? So now the satisfying assignment has moved to a random location. Okay? Now what am I going to do? I'm just going to run the solver on C tilde instead of C. And so if the solver worked on C tilde, it's going to find the satisfying assignment that's shifted, but then I'll just unshift. Okay? So does everybody agree that if the solver actually works on C tilde, that I would find a satisfying assignment for C? Hopefully that should be clear. But the question is, how do we make sure that the solver works on C tilde? Well, that's where we're going to use the IO guarantee. The point is, like, maybe C was like an arbitrary, circuit which had a unique satisfying assignment. But after I shift it and IO it, then what am I looking at? I'm looking at a circuit which has just a truth table which has a 1 in a random spot. IO security is going to say, well, the solver, which was supposed to work on random point functions, which were 1 in a random spot, and 0 everywhere else, well, I'm not going to be able to tell the difference between what was an obfuscation of a random point function and the obfuscation of the shifted thing. So the solver should work here. Does that make sense?
Sorry, so is it right that IO is now being applied to a randomized circuit?
So the circuit C tilde, okay, good. This shift is happening before I obfuscate. So I get a fixed C tilde. And that fixed C tilde I'm going to run in the solver. But the distribution on the functionality of C tilde is just a random point function. And so then because the solver worked when I IO'd a random point function, it should also work when I both. Gotcha. Okay, so then that's a little bit about how you go from average case solver into a worst case solver using the shift approach. And it turns out you can build on this to try and get an optimally secure one-way function. Okay, so that's a little bit about the complexity theory there. I guess our energy levels are dropping. So I will.
Why did you leave IO if you do the reaction?
Good. Okay. Right. Good. So what you're probably thinking is this. Oops, sorry, I went back too far. You're saying, listen, I re-randomized C. I got the C tilde.
Yes.
Its truth table is just a random point function, right? Yes. So my solver is supposed to work on random point functions, so I should win, right?
Yes.
But the problem is, even though C tilde has the functionality of a random point function, you need to make sure the solver might not work on those types of circuits, right?
So the average case is for the average case over all the circuits that computes the same.
So the average case is over the functionalities. IO essentially reduces to the functionalities. So as long as the
yeah. So the solver is works on obfuscated point functions.
Okay.
But it doesn't necessarily work on, without using the IO guarantee, it doesn't necessarily work on like these shifted functions.
So it's average over all point functions.
Average over all point functions. And you need the fact that
Point circuits.
circuits after you IO them. Okay. Yeah, I see. So the point is like these C tildes, a priori, the solver might not work on them. But because of the IO guarantee, IO says whether you work or not should just be dictated by your functionality. And because their functionality is random point functions, then it should be. Okay, yeah, any other questions? Okay, good. So now let me tell you about one more place where kind of like one more of these complexity arrows, which you might find interesting. And it's one of the complexity arrows that comes in trying to build optimal PRGs and also optimal public key encryption. And basically, it's another fine-grained issue. What'll happen is, you'll want to build optimal PRGs, and you can use IO to show if there's like some non-trivial attack on PRGs, you'll get a non-trivial algorithm for a unique set. So that part works fine. But, and now unique set is the decision problem where you're promised there's at most one satisfying assignment. And it's a decision problem. Before we said there was exactly one satisfying assignment and you had to find it. Here, there's at most one satisfying assignment and you have to decide whether there's 0 or 1. And the problem is, it turns out, we don't know how to, it's not obvious how you go from a non-trivial algorithm for a unique set into maybe a more standard assumption on complexity classes. And why is that? It's that because you could end up in the following case. Suppose you might have a polynomial time algorithm for a unique set, but its success probability is only 1/2 plus epsilon, where epsilon is really small, like 2 to the minus 0.51 n, right? You could end up in a scenario, and like if you want to, get optimal security here, that would mean security that's even in this like really small regime, and when you do the transfer with IO, you might get a polynomial time algorithm with this much success probability. And now you could just say, listen, fine, I'm willing to make this as my complexity assumption, that just like there is no polynomial time algorithm for a unique set with this much probability, but it would be nice to reduce it back to some statement about SAT, the original.
You relax P to function.
Sorry, relax P to
you instead of doing P different than NP, you do.
Oh, yeah.
So this is.
Yeah.
So now I see what they got.
Yeah. Good. Okay. So what can you do with this? Well, there are kind of two problems, right? This one is that you can't naively amplify success probability. Usually when you have an algorithm that works with some probability, like 1/2, let's say 3/4, you would just run it over and over and over again and then take the majority answer. But the problem is if you have a coin and it has bias 1/2 plus epsilon, in order to distinguish it from 1/2, you'll actually have to flip it 1/epsilon squared times. And I'll tell you about this coin problem issue on the next slide, but it turns out if you want to do success amplification, you have to pay 1/epsilon squared here, which is bad. So you can't amplify the success probability, so I don't know, you can't even turn this into like a non-trivial algorithm for a unique set that works with high probability. So that's one thing that goes wrong. And the second is you also can't naively translate this to SAT. If you try and run Valiant Bezirani on this, it's like you'll get n instances and then, but you only have guarantee like this, it's gonna kill you. So if you know what Valiant Bezirani is, great. If you don't worry about it. But I'm gonna focus in on this coin problem issue. So what is the coin problem issue? So the coin problem, actually this is not maybe what most people would call the coin problem, but this is what I'll call the coin problem. It says, let's say I give you query access to some function that maps a number between 1 and n to 0 or 1. And I want you to distinguish between the following two cases. Either the expectation of x is at most 1/2, or it's at least 1/2 plus epsilon. I don't care what happens in the between region. I just want you to distinguish these two cases. Okay, good. Does the problem make sense? And I want to minimize the number of queries I have. I let you make randomized queries if you want. And it turns out, this is like a classical result in information theory, that you need like beta 1/epsilon squared queries. Kind of the idea is every time you flip this, you expect to see like square root deviation. And so to beat the square root deviation, you'll need to go to 1/epsilon squared instead of 1/epsilon. Okay, so this requires 1 over epsilon squared queries.
This shows that the term of bound is tight. That the epsilon squared is the term
Oh,
of
yeah,
bound
it's
is tight. That's what-
Yeah. Good. And that's bad for us because if we wanted to work in this 2 to the minus 0.51 n regime, we don't want to square this epsilon. Ideally, we would just want 1 over epsilon. And it turns out that our idea to try and do this is say, okay, let's not try and solve the coin problem. Instead of trying to distinguish these two cases, let me ask how hard is, let's say I just want to certify that this coin is biased, So I'm allowing you to, and by certification, it means I'm allowing like a prover to hand me some information, and now I'm supposed to verify that, I just need to verify that I'm in one of the cases. Okay, and if you're familiar with complexity theory, it was actually going to be like an Arthur Merlin protocol, but if not, don't worry about it. And let me tell you a bit about how we do this. And to do that, I'm actually going to talk about an easier coin problem. So an easier coin problem, which maybe is closer to the traditional coin problem, is now I'm giving you query access to a function from the natural numbers to 0, 1. So before I only had the numbers 1 up to n. But now I give you the natural numbers up to n. And I'm going to say each output of f is just drawn IID, independent, identically distributed from a Bernoulli distribution with p. And I ask you to distinguish 1/2 from 1/2 plus epsilon. Okay. All right. And now, or actually, I don't ask you to distinguish. I ask you to certify. Let's say, how would you certify the 1/2 plus epsilon case? Anyone have any ideas? So, I get access to this potential stream of Bernoulli coin flips. And what I want is you're supposed to tell me some advice such that I can make, 1 over epsilon queries to this function and be certain, or quite fairly certain, that I'm in the 1/2 plus epsilon case.
Fairly certain or certain?
Yeah, you won't get 1. Yeah, so fairly certain. Let's say 2/3 probability here. You can't get 1 because these flips could have been bad. Yeah.
I feel like this isn't right because it's infinite. You can try to give them places to look where there are too many heads.
There's too many heads. Good. Yeah. This is a good idea. So what you will do is you're going to basically find some index on which there's a long run of heads. Okay? So you're going to find some I such that for 1 over epsilon coin flips, they're all going to be equal to heads. And now this is good because there's a question of whether this is actually a certificate. But if it was actually a certificate, that's great because I can check this with 1 over epsilon queries. Okay. Let me sketch the argument for, why this is a certificate. The analysis will kind of boil down to this. If I fix some I, what is the probability that, starting at that I get a run of heads? Well, if p equals 1/2, that's just 1/2 to the 1 over epsilon. But if p equals 1/2 plus epsilon, well, what do I get? Well, 1/2 plus epsilon to the 1 over epsilon. I can break out the part that's 1 I can factor that into 1 plus 2 epsilon times 1/2. I'll get a 1 over epsilon to the power on both sides. Well, use your approximation, that's e squared, and that's the same number as before. So there's an e squared factor difference here. So, as long as I choose my sufficiently good value of small here, I expect there to be with 2/3 probability, with noticeable probability, there's some constant probability difference between these two cases.
They're too small.
They're too small?
But the numbers, epsilon.
Okay, good. Yeah. So these numbers are really small. So what I will ask for is I'm going to ask for an I between 1 and 2 to the 2 to the 1 over epsilon when I expect, basically I'm going to pick the number such that, with probability 1/2, I'll hit this condition. And then I'll show that All right. I wasn't supposed to give you a full proof, but this is kind of the idea. Okay. And it turns out from this, what will happen is that you can get 1 over epsilon queries you can make and some non-deterministic queries or Arthur Merlin queries, really. What will happen?
And it's large enough, I guess, in terms of epsilon.
Good. we don't want to make that assumption. Like, okay, so on the previous slide, a big difference that happened was this was the natural numbers instead of the numbers 1 up to n. And you could run the argument from the previous slide as long as n is like, I guess, whatever, sufficiently large. But maybe you don't want to make that assumption. So if you don't want to make that assumption, what will happen is you'll actually have Arthur send over like a pairwise independent hash function, and you're going to simulate there being more coins flips than there actually were. And it turns out that this works without assuming n is sufficiently large. Although it is kind of strange because it's like, I don't know, as a protocol, it's like I have n coin flips. I'm going to pretend that there were more coin flips than there actually are using pairwise independence, and this is going to help me, which is a little strange. And one thing related to that is like in this Arthur Merlin protocol, like Arthur has to send over 1 over epsilon bits in the first stage because he needs to send over like the keys to like some they're not even pairwise independent, they're more k-wise independent for large k, and then he needs to send over actually a lot of bits in the first stage. It'd be nice to reduce that or show it's optimal. Okay, great. So you can do this, and this, if you're familiar with complexity theory, like this gives you a quadratic improvement in Goldwasser-Sipser set lower bound protocol, which for our purposes was useful, and it lets us actually put in this question mark, a non-trivial algorithm for non-trivial algorithm for NP versus co-NP. And yeah. And so the last thing I wanted to talk about is I wanted to say a little bit about direct product hardness for SAT, but we're at the last minute mark. I just had one slide on this, but basically what you can do is you can reduce IO, you can use IO to turn like direct product hardness for one-way functions into like direct product hardness for SAT, which is like for k-fold unique search SAT, which is I give you k circuits that are all promised to be uniquely satisfiable. I want you to find satisfying assignments to all of them. And the naive algorithm runs in like t over 2 to the n, because that's my chance of hitting 1 to the power k. And it turns out, if you believe in IO, this you can reduce like the optimal hardness of, or you can show that this is actually optimal, assuming like NP versus co-NP as optimal hardness.
So you don't have t to the k, you still get only t. The k applies only t.
The k apply. You're saying you should hope that
in the naive one, but what you really want is poly t over 2 to the n k.
Poly t. You're saying there's a better algorithm that does poly t over.
No, I am saying that that's what you want.
That's what you. Oh, I see. The hardness you want. This would be optimal. And you get it. But I don't want to. Good. And if you look at stare at these parameters long enough, what you'll see is that you get over there.
Also, the success probability is like 2 to the minus nk, which is much less than 2 to the minus n. So you need non-determinism to make use of that.
Good. Exactly. Yeah, that's a good intuition. Although, I don't want to say. Good. That's great intuition. But one thing that's weird about this is that like this reduction, which is like something about direct product hardness of SAT and NP versus co-NP, it like uses cryptography IO in there. Can you do this without cryptography? Next question.
Well, you mean the second arrow uses IO as well?
The assumption is IO.
Right. So basically to do, this is what the second arrow uses IO. Because that second arrow is this result. Good. And, there's some missing complexity theory. Okay, sorry. All right, I'll try and be quick here. So here is a problem. It's called the lossy function problem. You're given a circuit C that maps n bits to n squared bits, and you need to decide, is it 1 to 1? Is its range equal to 2 to the n? Or is it like kind of very much not 1 to 1, and that its range is at most 2 to the n? Is at most half of what an injective function would be. And I don't know how to relate this to standard complexity assumptions. If you're familiar with the class SEK, it kind of smells like SEK. I can tell you about it later. In fact, it's like some problem that has like perfect completeness SEK or something like that. So it'd be great if you guys could figure out if this problem is hard. And then another problem is this correlation finding problem. Let's say there's a function that maps n bits to m bits. Maybe it could be hard to compute. And you're given a circuit C that maps n bits to m bits, and you want to find an x such that C of x equals f of x. Don't worry about this, but my conjecture is that for every possible f, even ones that are hard to compute, f correlation finding is not in P. But I don't know how to show that. We'll reduce it to some complexity assumptions. And if you could do either of those things, it would have some nice crypto applications. So thank you guys very much. Yeah.
Questions, comments?
Like what's the last slide about correlation? You're just asking to find the name.
It's like intersection or something.
It just matches. It's this what you'll get on the crypto side is something called correlation tracker.
Sorry, you're given C, so F is fixed.
Sorry, yeah, F is fixed.
Okay.
Yeah, there's actually a sequence of F, and then you can define this problem, which is F correlation finding, and they correlate if they have something about which they
Isn't this the match?
Yeah, I called this the match function. Yeah, good. Yeah, good throwback. When in my
Open problem.
yeah, exactly. Yep. All right.
Okay, thanks for the wonderful talk.